Scientists are in the prediction business, and as we'll see, predicting the future is hard work. But as scientists, we have something even better than a crystal ball to help us peer into the future. Hi, I'm Jeff Grossman. In our course on the science of tomorrow, we'll look at the ways science and technology may change the fundamentals of the way we live, what we eat and drink, how we travel, how we learn, how we communicate with each other, how long we live. But in order to separate fact from fiction, we first need to understand something about the way science works. Science operates through a rigorous process with lots of checks and balances, but there's also plenty of room for creativity. In fact, coming up with creative ideas is one of the most important things a working scientist needs to do. It may be helpful to think of science as a game. Let's take a look at how it works. Like any game, science has a very well-defined set of rules. It's just like checkers or chess, only particular moves are allowed. If we don't follow these rules, we're cheating at the game. And most importantly, we don't have much chance of achieving our goal and winning the game. For science, the goal is to enhance and improve human knowledge of nature. Our game is called the scientific method. In this method, we begin by asking a question, like, why are leaves green? We then look up everything we can that's related to the question at hand, like how trees grow and what makes color. And at that point, we can construct a hypothesis to try to answer our original question. Sometimes the hypothesis is little more than an educated guess, while other times it's based on complex deduction. But either way, the next part of our game is to test the hypothesis by carrying out an experiment. Let's say our hypothesis was leaves are green because trees are brown and the colors look nice together. Well, in that case, an experiment you could do would be to find trees that are not brown, but a different color, and see if the leaves are still green. You would then analyze the results of your experiments and draw conclusions. In this example, you would find the hypothesis to be false, and so would go back to creating a new hypothesis. If your hypothesis was true, then you would report your results. Not that this would mean that you found the correct answer, but rather that given your data, you've shown that a given hypothesis could be correct. Then further experiments are done. Other scientists repeat or expand on your original question, and so on. Now, sometimes an experiment cannot give a conclusive answer, simply because the scientist didn't have the right tools to perform it. In the effort to obtain a more accurate answer, technology steps in to develop new tools, ones that improve crucial aspects of the experiment. For example, suppose that in our experiment we cannot distinguish closely enough between certain kinds of green and brown. Since some leaves are sometimes in between in terms of their color, this poses a serious challenge to our data collection. In order to make better measurements, we'd need an instrument that can quantify the color in a more objective way. That drives new technologies, which in turn lead to new scientific understanding, which further drives technology. Of course, technology isn't limited to serving only science. For example, because we know what determines the color in leaves, namely the presence of water and a complex photosensitive molecule called chlorophyll, we can and indeed have exploited this technologically for many applications, from dyes in clothes to understanding the chemistry of food to making better solar cells. Okay, back to our discussion about the scientific method. The rules and checks and balances laid out in this process are not only designed to keep us honest, those checks and balances are also what stimulate us to refine our ideas and to continually ask new questions. So, what happens when we violate the rules of the game? Let's look back at what happened in the pre-scientific era, before the rules of the game were even well developed. We've all heard of the Black Death, the horrible plague that wiped out between 30 and 60% of Europe's population in the middle of the 14th century. With their friends and family dying all around them, people were terrified and sought to find an explanation. Many thought it was divine retribution for the sins of humanity, and groups of people known as flagellants would walk from town to town whipping themselves in atonement. Others tried to lay the blame on outsiders or minority groups. Jews, for example, were accused of poisoning wells. Scholars at the University of Paris, after a serious investigation, concluded that the plague was caused by a combination of earthquakes and astrological forces. Given the seriousness of the threat to their lives, we can only assume that the people of that time were seriously motivated to come up with good answers. What they lacked was a method of testing their theories. To put it simply, the close iterative loop that science uses to describe the world was not followed. Baseless rumors got traction through word of mouth and gained currency as truth. Eventually, by following the scientific method, with tests and trials and validations, science found the real cause of the plague, a very tiny bacterium that was brought to Europe along trade routes from Asia carried by fleas on rats. Once the cause of the disease was understood, it was possible to make more rational plans for prevention and treatment. And understanding the real mechanism of the disease unlocked a new world, microbiology, and its incredible potential along with it. As we'll see, understanding the inner workings of these microorganisms, all the way down to their genetic code, allows us to apply our scientific knowledge to develop a whole range of new technologies, like making fluorescent bacteria, or organisms that can produce fuel, or synthetic life itself. The potential is enormous, and not only in terms of understanding, but also for technological and human progress. In simple words, a complete understanding of the real cause and effect, enabled by science, allows for technological progress to be made. New opportunities arise, as well as new challenges, some of them unpredicted, and the game starts all over again. Even in modern science, sometimes we have data that we don't want to recognize at first, because we don't understand what mechanism of action could account for it. But these are often the very things that lead to great scientific advances. In fact, many of the scientific advances over the last several centuries were initially regarded as controversial by the general public and often by fellow scientists as well. When quantum mechanics was proposed, many were skeptical. The idea that a particle, or any object really, could behave as a wave was considered almost insane. But that very same idea and the theory as we now know it is the foundation of much of the technology we make and use today. Without quantum mechanics, we wouldn't have the revolution in information science, and therefore the development of the internet. We wouldn't have superconductors and artificial intelligence machines that make robots smarter, allow for the prediction of new materials, and diagnose medical conditions more accurately. All topics we'll be discussing throughout the course. Without quantum mechanics, we wouldn't have been able to build powerful new microscopes to probe nearly anything, from the electrons in the solar cell to the neurons in our brain. And we certainly could not even dream about magnetic levitating trains. Now, quantum mechanics is quite a striking example. Of course, the level of weirdness that a scientific theory has does not tell us much about its veracity. For that, we have to go back to our game, the scientific method, and start the round of experiments. There's really no shortcut. And as in any game, a referee is required. The final step in the scientific method is to write up your experiment in a report, describing your ideas and what methods you used to test them. The report is then presented to peers at conferences and/or published in journals. This results in feedback and discussion of the findings in the report itself, which then leads to further experimentation with new questions or new experiments or new hypotheses. Of course, progress is only made possible by the work done by others before us. For example, Einstein's theory of relativity, which combines and explains the fabric of space and time as woven together, wouldn't have been possible without Newton's analytical laws of mechanics. These laws were in turn not possible without Galileo's formulation of the laws of motion. So the literature is the starting point for any scientist who wants to know what the state of the art is in the field. As scientists, we know we can rely on it because it was the result of the same game we're playing today, with the same rules. Does this mean we should not question these results? Of course not. After all, the science is all about asking new questions. But such questioning, of course, always should be done following the rules of the game. Take the theory of evolution, which was formally proposed by Darwin in 1859 and was the result of decades of observations. These ideas were scrutinized and reviewed to the full extent. Some still think that the modern theory of evolution is the same as that proposed by Darwin, but that's actually not true. Although the basis for the theory of evolution is the same, the theory itself has evolved tremendously because that is in the nature of the scientific process. For contrast, let's take a look at a couple of recent examples of theories that turned out not to be winners and figure out where they went wrong. First, the famous case of cold fusion. Cold fusion was proposed in 1989 as a very inexpensive way to melt atoms together to release huge amounts of energy. Nuclear fusion, which exists and is in fact what powers the stars, requires extremely high temperatures. The new theory suggested that the same process could be obtained at room temperature, thus the cold in cold fusion. If this had been true, the consequences would have been enormous in terms of energy production. But it turned out that the rules of the game had not been followed. In particular, the claims of the successful reaction were never backed up by accurate experiments, nor replicated or confirmed by independent teams. Eventually, articles were published debunking the claims as myths. What went wrong? In this case, the scientists did not subject their theories to the kind of rigorous tests that could withstand the evaluation of the referees. Cold fusion was never actually observed. However, a quick search on the internet will prove that the myth of cold fusion is still alive and well. Many people still believe in it, even more than 20 years after it was disproved. Why might this be a bad thing for science and for humanity in general? Because it deflects attention from constructive theories that could help us actually build something. The fact that we cannot prove that cold fusion exists, of course, means that we cannot reliably build a reactor with it. But luckily, science didn't stop with mythical cold fusion. In our lectures on energy topics, including nuclear, biofuels, solar cells, batteries, and hydrogen storage, we'll talk about how a reliable, sustainable, and inexpensive source of energy is very much needed. Clever advances in solar energy and energy storage, and even perhaps someday not so cold nuclear fusion, may provide the solutions we seek. Let's look at a different kind of example of a scientific theory that has turned out not to be a winner, namely homeopathic medicine. At its heart is the conjecture that water retains a memory of the substances that were once dissolved in it to some specific dilution. Scientists claimed to have found proof of it. Following the scientific method, they submitted their work for publication. Now, a scientific journal is not a blog or a tweet. If you submit a piece of work, it will be reviewed in great detail, especially for topics so potentially revolutionary. This is what happened with the water memory concept. When reviewers were asked to have some of the experiments repeated, nothing definitive could be proven. In other words, water didn't seem to have any memory. The paper was rejected. But was this the end of it? In the specific case here, the experiments that were done were not analyzed correctly, and the results were used only to justify an assumption. This is an important point. Sometimes scientists, who after all are people with feelings and personalities like any other, will make assumptions and look for any possible way to make them believable. This is what happened for the memory of water debacle. But because these unproven assumptions were nevertheless considered true by the researchers who proposed them, the story didn't end there. In fact, a new myth was born, and one that has led to quite a bit of profiting as well, as anyone who goes to a local supermarket can attest. So, Even though homeopathy today is very well known and widespread, there is not a single scientific experiment that has ever been done to validate its benefits. This doesn't mean that homeopathy won't in some cases cure someone, but the cure is most likely a placebo effect, which is a very well-established clinical and scientific theory. So we can safely categorize the memory of water and homeopathy as myths, not science. While on the topic, the placebo effect is an excellent example of how very little we know about our brains. We have about 100 billion neurons in our brain, each neuron with thousands of interconnects with other neighboring neurons. As we'll see, we are only beginning to understand how it works. And even the most powerful computers we know how to build, ones that can perform trillions upon trillions of operations per second, pale in comparison to the brain. The more we understand about our brain, the more we'll be able to learn from it, whether that means making faster computers, or better predictions, or new forms of artificial intelligence that can understand for the first time nonverbal cues, which, by the way, make up a whopping 90% of all of our communication. And speaking of 90%, that's also the amount of our brain that some people claimed somehow goes unused. Just like cold fusion and water memory, that's a myth too. As we can see in the water memory example, if a myth is persistent enough, it can eventually develop into a pseudoscience, only masquerading as science. There are many other examples. Probably the best known pseudoscience is astrology. Pseudosciences often mimic real science. They have theories, they make predictions, they perform measurements, they analyze data, and their experts make presentations to peers. The difference is that pseudosciences rest on assumptions that simply cannot be proven. For example, you might have read your astrological prediction of the future in the local newspaper. You might have liked or not what you read. But later, if you look at the success rate of the prediction, you'll find that the chances that the predictions are right are essentially the same as pure coincidence. This is the problem with confusing pseudoscience with science. Predicting with scientific accuracy means that one can go back to the predictions you made and know that they were correct, at least to some extent. To better describe this concept, as a mental exercise, examine anything you suspect may be a pseudoscience and see if you can identify the point at which you cannot rationally explain it and you need to take a leap of faith. Right there, is where science ends and myth begins. Because of the disconnect with reality, a myth or pseudoscience is not likely to translate into scientific progress. But that doesn't mean that a myth is always a bad thing. As long as the boundaries between myth and science are well defined, the two can, and in fact do, go hand in hand. Take, for example, the evolution of robotics. When the assembly line was invented by Ford, many thought of a future where machines could make themselves. We'll talk amply about this process later in the course. But for now, let's just say that that mythical idea eventually turned into reality because of the way science evolved. Machines make machines these days, and we'll provide many examples for why we need that, to make assembly more efficient and to make things smaller, as we'll learn about in the nanotechnology and microscopy lectures. A myth became reality because of science. And scientific and technological advances stimulate the contemporary culture to think about the extreme consequences of each advance. Eventually, in some cases, these extreme consequences are destined to become reality. Many of our modern gadgets were predicted by popular culture 50 years ago, like the cell phone, personal computing, e-commerce, plasma TVs, and MRIs, to name only a few. Still others, like the teleportation in Star Trek or the flying cars of the Jetsons, are, at least for now, still science fiction. These two examples just happen to both have to do with transportation, which, as we'll see in that lecture, has suffered from the fact that an energy revolution, similar to the information revolution, has not occurred. Still, there are many possible technological revolutions that await transportation, from levitating trains to much more efficient airplanes and cars. Sometimes, myths are a way to express a vision for the future, often based on an unrealistic extension of a scientific or technological theory of the time. This can be mere wishful thinking, of course, but sometimes a myth can serve as motivation and inspiration. A major leap in scientific advancement is what is required to get there. For example, back to Star Trek and transportation. Scientists are working on the concept of teleportation, which recently was actually demonstrated in the lab for tiny quantum mechanical particles. So perhaps in another 50 years and a few more sci-fi TV series, we'll finally be able to say, beam me up. And sometimes even good science can produce a fantasy that is never fulfilled. Not because of a lack of scientific merit, but for other social, economical, or environmental reasons. For example, flying cars that rely on nuclear power were expected someday, given the availability of nuclear power in airplanes. Why don't we have them? Cost is certainly an issue, along with environmental concerns, safety issues, and policy issues. Then there's the question of where we'd get the uranium. So we're not likely to see flying nuclear cars or any other kind of nuclear-powered car anytime soon. But the nuclear example brings up another important piece of the puzzle of scientific myth versus reality: public reactions. After the recent nuclear disaster caused by a tsunami in Japan, entire countries, including Germany and Italy, have declared that they will go completely nuclear-free in the near future. These are not necessarily decisions based entirely on scientific grounds, but rather on a combination of uncertainty and understandable fear. Now, back to reality. We started out by saying that science enables technological progress. How does that happen exactly? Through scientific discovery and understanding of how nature works, we find new ways to mimic nature or improve upon it. This is what technology does. But it also enables new science to be done. Take, for example, the development of the microscope, which happened because of the scientific understanding of optics, which in turn enabled the formation of new science, like the fields of biology and nanotechnology. Science and technology are closely interconnected with each other because the evolution of one relies on the parallel evolution of the other. In the coming lectures, we'll see how this close connection has affected us over time and how it will affect our lives in the future. We'll talk about how we can make magnets that levitate frogs, how we might grow our fuel in the future, how science and technology will give the planet its food and water, and how computers, robots, and artificial intelligence will change the world. We'll cover how we move from one place to another, and how we move not just people, but also vast amounts of information through every square inch of the globe. We'll talk about energy, how we'll be making and storing it in the future after fossil fuels have had their run. We'll discuss nanotechnology and how the power of small will serve as the basis for so many of our future technologies. We'll learn about how only recently we've been able to make microscopes that see things as small as the nano world, and what that means for the future. We'll talk about the basic building blocks of life, how to engineer them, and how viruses could one day be not only the most important cure of diseases, but also a vehicle for making new materials. We'll learn about the brain and how it might interface with technology in the future, and how one day we may create entirely new forms of life itself. Throughout all of these exciting topics, we will highlight myths as well as misconceptions. But one thing is for sure, myths tend to solidify and remain unchanged over time, to the point where they become irrelevant. Science, on the other hand, never stops advancing. That's the beauty of it. And people joke that half of what we think we know may not be true. The problem is in knowing which half. But there are some basic laws of nature that we know will hold true. And in this course, I'll try to lay those out as clearly as possible. I could have chosen 24 different topics, of course, because science is a vast endeavor. Part of what I hope to convey, in fact, is just how grand the enterprise is. Inevitably, these topics reflect my own interests. In my group at MIT, we work on understanding and designing new materials for a wide range of potential uses. We first design these materials, atom by atom, using complex computer simulations to tell us what the properties will be. And then we make the ideas real in an experimental laboratory. We focus on making new materials for more efficient and cheaper forms of energy conversion and storage technologies, for new ways to desalinate and clean our water, and for new approaches to detection, all the way down to the tiniest of molecules. My group is in the Department of Materials Science and Engineering at MIT, which is a department that purposefully mixes different disciplines together, from the physical, chemical, mathematical, and biological sciences to all areas of engineering, all in one department. My own background is in theoretical physics, since I've always loved how the basic physical laws of the universe provide the foundation for explaining the world. But my real passion is in turning fundamental understanding into something relevant, something that could make an important and positive difference in the world. Materials science is, well, it's all about materials. And given that so many of the future challenges our world faces, from clean energy to clean water to fighting disease and a cleaner environment, so many of these challenges at their core can only be solved with game-changing advances in new materials. That's what keeps me up at night. That's why I get so excited, that I get to work on understanding and designing new materials, all the way down to the scale of the atom and electron, and all the way up to the scale of a new solar cell or car battery. For millennia, science has given us knowledge of how the world works, that led in turn to more magnificent discoveries and extraordinary innovation. As a result, we enjoy higher standards of living and live much longer and healthier, have a greater appreciation for the wonders of our universe, and can be inspired in new ways that challenge and extend our imaginations. And yet, rarely, if ever, has there existed a role for science and a scale for science and an absolute need for science as there exists today. The problems we face now are global in nature, not local. The problems we face now will have long-term consequences, not short-term. The problems we face now threaten our entire way of life and indeed life itself, not just a small part of our lives. And the problems we face now have an urgency to them we cannot afford to test. As a human being, a husband, a father of 3 small children, and a concerned citizen of this wonderful planet, I can say that I'm deeply worried. As a scientist, on the other hand, I am deeply motivated, intensely challenged, and passionately engaged. This is a pivotal moment in time for science, a moment when, if strongly supported by government, our industries, our investors, and our people, science research can solve these problems, meet the challenges we face head-on, and fundamentally change the world.